Hi guys, welcome to my video. This is the third video on GD&T. Right, some of the things we're going to go into today. There's different ways to apply the GD&T symbols. It's important to understand whether the symbol applies to the surface or the center line or the medium plane of the feature. Which are the best features to pick for datums, some tolerance combinations, common zones, whether or not you need to use rotational datums as well as your normal first two datums or not, a little bit about projected tolerance zones, minimum and maximum material requirements. I also had some questions on the first two videos that I did about what a DTI was. So I thought I'd just put a quick slide on a DTI and where you use them. Some people know, a lot of people know what DTIs are. Just in case you don't, there's a slide there just explaining what a DTI is. Right, applies to a surface or a medium plane. So we can see this example on the left. The GD&T symbol isn't lined up with the arrow. So in this case, this would apply to the surface, not the center of this feature. This is being applied to the surface. This is being applied to the surface. This is being applied to this surface. In this example is at the bottom. The symbol here is lined up with this arrow. So this means the center line of this feature. So this is being applied to this center line of this feature because the arrows are lined up. Likewise, this is the same. This is the same. So we've got some datum examples on the right. Datum A being applied to the surface. Datum B being applied to the surface. But in this location, datum A is the center line of this diameter. So the center line, datum A here, is actually from this point here to this point here. It's this cylinder, the center line of this cylinder. Got an example here. Datum A is the center line of this feature and the center line of this feature for B. So in this case, you might be machining something relative to this center line and this center line. And then we've got some sort of cutout here, and again the center line of B is the center line of this feature, so it's actually the center line here. If you want to apply a datum just to a certain portion of the surface, you can do it using this method. We can see here the datum's being split evenly, so you've got A-B, and that might be used in this situation. So you might be machining this surface here, for example, relative to the center line of this and the center line of this. So what that really means is when you set this part up to machine this surface, you set up this datum and then you move the part around to get this center line in line with this center line, and then you machine the surface, for example. Okay, so I think that one covers the differences between the surface and the center of the feature, or the center line of the feature. Got a couple of examples here. We've got some sort of block, 50mm dimension, and then we've got datum A is applying to this surface, and we're making sure this is parallel. This surface is parallel to this surface with this symbol here, parallel. And this surface has got a flatness on it. This is the normal way of setting up datums or faces opposite to datums that are important. So this is an example of not the best way to do it. So here, datum A is lined up with this surface. So this is not correct because we want datum A to be this surface in this case. This actually signifies datum A as being the center line of this feature, which is not what we want. Likewise here, this is lined up here, it doesn't want to be lined up. And also, we've got a flatness of (1) and a parallelism of (1). But in this case, we don't need the flatness because this one's actually doing the flatness of this surface for you, and it's making sure this surface is in line with this surface, or parallel to this surface. So this is doing more for you. You don't need this at the same time. You only need a flatness on this side if it's a better figure than what you've got here. Sometimes it can be quite difficult for manufacturers or people to understand whether you're talking about the center line of a feature or the surface of a feature. Sometimes they don't understand this very well. So when you're doing a drawing, sometimes it's better to indicate when you want the center line of the feature using this sort of method. So in this case, this would be an ISO drawing. So we've got brackets around the datum A. On an ASME drawing, I don't think you need the brackets. You just put datum A in again. So again, there's some slight differences depending on what standard you're going to use. So the actual part geometry matters a lot on the correct datums to pick or the best datums to pick. So in this case, we've got this component here, and we've got a diameter here and 2 diameters at the end. So in this case, this surface from this point here to this point here is quite long. So it's 203 millimeters long from here to here. So it's quite a long surface. So this is an ideal surface to pick for datum A, especially if it's an important surface, and it is because we've got a surface finish symbol here, likewise here and here. So this surface is important to be as good as possible to this surface and to this surface. So in this case, this part's been set up. Datum A is the center line of this diameter. And we've also got form control on this cylinder. So we've got cylindricity, and it's very tight cylindricity. And then we want to make sure that this end and this end run true to this diameter. So in this case, we only really want or need one diameter, this diameter A. Because it's such a long surface, controlling this to this is the best way about going about that. So in this case, we're making sure this surface has got a total run out to this surface, and this surface has got a total run out to this surface. So this needs to be round, square. This total run out is doing a lot for you in effect. And we've got the same on both ends. And also we're making sure that these side faces of this cylinder are also tightly controlled. So this total run out here would also control the flatness of this face, the squareness of this face, whether it's dished or bowed. So it's doing a lot for you again on both sides. So probably a bush comes along here, it sits on this surface and it pushes up against this surface. So it bottoms out on this surface, probably looking at how the way this has been detailed. So that's quite a good way of doing it, where the surface, the datum surface is very, very long. It's good datum to pick, and it ensures both ends are controlled accurately to this surface. So in this case, we don't really need a datum B for this component. Right, so we've got another component. So this is quite an important concept, and it's about how we control the center line of the component. So originally we've set up datum A. So datum A is this surface here. So this is a diameter, this is a diameter, 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 and this is the face, and this is a spigot diameter. So we've got a face here, and obviously it goes round. So it's the same face here as here, and that we've got a flatness on it. So setting up that is quite important. Obviously when this part goes on to the next component, it bolts back against this surface, and the bolts probably go in here. So the bolts are going through here, and it's going to get pulled back on this surface. So this surface is quite important with how the part sits on assembly. If this surface is not square to this surface, it could throw the end of the part out quite significantly. So it's better to use the primary datum as this bolting surface. And then the spigot, because the spigot's only very, very short, it's better then to use this as datum B. Because this is the primary datum, this center line is always square to this surface. That's how the GD&T works. And then we're positioning this center line using this diameter. So this is only a very small diameter, so the diameter of the center line is only here somewhere in effect. Yeah, because it's only a very small surface. If we use datum B as datum A instead, and we use this as the primary datum, any squareness error from here to here can throw this end out massively, because this is only a very, very small surface. So a fraction error in outer squareness here, the center line would then be treated there at an angle, and then the center line could be thrown out massively at the other end. So it's quite important to use datum A here as the primary datum. And this is how you set components up a lot when you've got bolting faces like this. And again, it does matter on the part geometry. It takes a little bit of experience which datums to pick first and second. But generally, if you look at how it's going to get bolted back on assembly, that will sort of tell you which you want to use first and second as your primary and secondary datum. So the first datum's got this flatness tolerance on it, which is good. And then we've got datum B here. And datum B's got a form control on it. In this case, we've got a roundness figure. We probably don't really need cylindricity because this is only a very, very small length. If this was a lot longer, we'd probably have cylindricity here instead. But because it's only very, very short length, the roundness is probably fine. But then also we need to make sure that this diameter is square to this face. There's always going to be potentially a small error, but we want to make sure we minimize it. So we've got the squareness value here, we've got a diameter 0.02 to A. So we're making sure that this is square to this. And this is sort of some things that people miss when they first do detailed drawings. They forget to tie in one datum to the next datum if it's important. In this case, it probably is quite important. And we've got a squareness diameter 0.02 to A. So that seems fine. And in this case, we want to make sure that this is square all the way around the part. So in all angles, all directions, which is why we've got the diameter symbol here. So it's square in all directions. Right, it looks like then we're machining some of the pads here. We've got an important pad here, looks like, and an important pad here as well. In this case, we've got a total run out to A, B. So A is your primary datum, B is your secondary datum. So this center line running through here is really centerline AB. And that's quite an important concept to understand. The centerline isn't centerline B, it's centerline AB. And that is very important to make sure that this centerline is always square to this face first. So here we've got a total run out 0.01 and 0.01 here. So this surface and this surface are important to this face and this diameter. When we bolt this back, this will get pulled back first. And that will position this end more actually than this datum really, than this diameter. Has more effect on the straightness. Okay, so we've got tolerance combinations. This is a combined tolerance here. So how this works, there's actually two tolerance zones on these holes, and that's what this is trying to show you down here. So it looks like datum A is the face, so that's probably the correct thing to do. The face that you're drilling into is the important face first, and then we've got B and C. So in this case, there's two tolerance zones. These holes need to be accurate to themselves within this bottom tolerance, and also it's to the front face as well. So these holes need to be very accurate to the front face you're drilling into. So they need to be in effect very, very square through this distance within this value here. But it's also controlling the pattern relative to itself in this direction and in this direction. So the 30mm dimension and the 35mm dimension sort of come into this box here, and also the squareness relative to the top face comes into this bottom box. But then we're saying the actual pattern relative to B and C can float a little bit more. So the pattern relative to itself is very, very tight with this figure here. It's also very, very tight with the squareness to the front face, the top face, which is what the bottom one's doing. And then also we're saying the patterning itself has to be relative to this face and this face within this top tolerance. So the pattern can float a bit more this way, and it can float a bit more this way. So this 15mm dimension and this 15mm dimension here come into this top box more. And that's basically how these tolerance combinations work. You have to satisfy this one and this one at the same time. Okay, common zones. So common zones, used on flatness a lot. I think this bottom example is very, very good. So basically what we've got here, we've got a surface here, here and here, and they're on the same plane. So this is where common zone, I believe, makes a lot of sense. And what we're saying is, you can't measure the flatness of this, then measure the flatness of this, then measure the flatness of this. Be treated at the same time. So you need to measure the flatness as one zone coming across. So the offset is a total from there to there of 0.1 going straight across the 3 pads. And all of them pads has to fall within that 0.1 all at the same time. It's not treated as a flatness on this face and this face individually. It's treated as one zone, and it's called a common zone, and it's done like this. It's shown like this. This top example, don't particularly like this top example. I think if I was detailing this top example, I would put a box dimension from this pad to this pad at this location here, whatever that's going to be. Put a box dimension on that, and then change this to a profile tolerance. I think that's the way I would show this, because I think it makes more sense and people will understand that better than this example. Okay, so whether you need a rotational datum or not. This is quite a common question. It comes up all the time. If you've got more than one pattern of holes in a particular job, do you need a rotational datum to link one set of holes to the next set of holes? And generally speaking, it depends. I think the standard, if you read the standards properly, if they're on the same center line, you don't need a rotational datum. If the tolerance is in the tolerance control frame are the same, i.e. A, B and C, or A, B in all of the holes. If you've got some holes that are relative to AB and some holes relative to BA, then it's 2 patterns. But if you've got multiple patterns in the same face of a component, for example, they would all be treated as one pattern if they've got the datum sequence the same. So if that's the case, you don't need a rotational datum. I think generally speaking, I wouldn't use a rotational datum if the holes are in the same face and you want the holes relative to each other. You don't need a rotational datum. It should be treated as one pattern, and that's basically what the standards are saying. I think if I was doing holes in one end of a component and then holes in another end of the component, even if they're on the same center line, I would actually link one set of holes relative to the other set of holes with a rotational datum on one end of the part. I think it aids clarity for whoever's coming to inspect it on what the requirement is, rather than them missing the requirement altogether. So I think I would go slightly different to what the standards say there. I would just make it doubly sure that they are linked in, if I need them linked in, if they're in opposite faces, but on the same center line, for example. Right, projected tolerance zone. This is actually quite important. It matters a lot more where your bolts are long or you've got studs in a component. So on a car cylinder head where you've got the studs sticking out, the cylinder head for example, and you're trying to put the cylinder head on, this is quite important how you detail this up. And the important bit here is you're basically detailing the length of the stud in effect to make sure when you put the cylinder head on that the stud is all within the tolerance that you're after. The problem is with the way that the GD&T works, it's the squareness that gives you the problem and why projected tolerance zone is so good. So for example, these holes here, if these were a lot longer, you'd probably understand the problem. So if we put a positional tolerance on this particular hole, the positional tolerance works from a circle at this location and a circle at this location, and it's the center line of that. So if we go, if we produce this hole and it's within tolerance, but the diameter is 0.4, 0.4, and it's going from extreme to extreme. Now that might be okay for the actual hole itself, but if you project that along the length of the bolt or the length of the stud, when you get to this location over here, it's a mile out, or it can be a mile out, which means when you come to put the cylinder head on, the holes won't line up with where the end of the stud is, which is why this is a good method. So it's usually used where you've got longer studs or bolts, but in effect it really should be used a lot more than it's normally seen. So here, this P60, this is the actual tolerance zone that you're after. So you're really checking your circle at this location and your circle at this location based on this hole. And this is the way to do it in the tolerance control frame. You just need to add the P in a circle next to the tolerance, and you need to tell them how long that projected tolerance zone is, and it's based on this hole. Okay, so maximum material requirement, this is used quite often. It's a very, very good way of giving manufacturers more tolerance. if they manufacture the holes not to the smallest size, for example. So whenever you're working out positional tolerance, you always work out the worst case scenario. So basically you're looking at the hole when it's at its smallest size and the bolt when it's at its biggest size, and that's when you work out the positional tolerance. The reality is, when the manufacturers make them holes, they might not be at the smallest size. So in this case, we can allow more tolerance, more positional tolerance on that particular scenario. And that's what the maximum material requirement, where it comes into its own really. So I put 3 examples here. Got example number 1. So we've got some holes, diameter 10, and we've got a tolerance. And here we've got positional tolerance with a max material symbol. So if the hole is produced at 9.9, which is the smallest size, we give the position tolerance of 0.04. So that's what you have to achieve. So if this hole is at its smallest size, 9.9, then you have to achieve 0.04 positional tolerance, which is very difficult. It's quite tight, that. However, there's quite a big tolerance on this. We've got plus or minus 0.1 on diameter. So if the manufacturers produce this hole at 10.1, then this actual tolerance here then changes to 0.24, that extra 0.2 we're using at this location, because the bolt's got more clearance and it's allowed to float more before it hits the sides of the hole. And that's the way this works really. So if I was to manufacture something with this on it, what I would actually do, I'd aim towards top limit for the hole. So I wouldn't actually go for 10.1, but I might use a manufacturing method that gives me a consistent size of 10.07, 10.08, very close to the top size, and then it's giving me close to the maximum positional tolerance allowance, and that way it minimises my non-conformances on the part. Okay, so this maximum material has been applied to the actual tolerance at this location, the 0.04. We can also apply this at different locations. So we can apply this into the datum symbol here. And basically what this means is it's usually where you've got a diameter, a spigot diameter, and the spigot diameter, if it's smaller and it allows more float, then you can allow more tolerance here as well. And that's basically the way it works. So the example here, got datum A. Datum A, so it gives a diameter of 99.95, which is within this tolerance. Then we have the 0.04 positional tolerance. However, if it is bigger, it's 100.05, which is the maximum size here, then we add that 0.1 tolerance to this size. And we can also use a combination of maximum material here and maximum material on the datums as well. You just need to be a little bit careful using max material on the datums. I don't normally recommend it. And what you don't want is, for example, the manufacturer to take an average size and give you an average size and then use max material on that average size. That shouldn't happen. It's not within the rules for that to happen, but I have seen it happen a few times in the past, so you just need to be a little bit careful. So basically this maximum material, it can help with manufacturing cost, but you should only use it where the maximum material affects the position of the hole or the feature. So for example, here I've just put a comment, it shouldn't be used on tapped holes or interference dowel holes, for example, because the tapped hole is driving the position of something, and making that tapped hole slightly bigger, it's not going to change the position. You're not allowing more clearance for the bolt to go through. So it shouldn't be used on tapped holes really. And interference dowel holes, it's not the size of the hole in this case that drives the position, it's the size of the dowel that gives you the tolerance. So it shouldn't really be used on interference dowel holes. You can use it on the clearance side for the dowel hole and on clearance holes. So maximum and minimum material requirement, when can we use it? So anything to do with size, we can use it basically. So we can use it on straightness, parallelism, perpendicularity or squareness, angularity, position, concentricity and symmetry. And this is just another example of using that bonus tolerance, if you like. But it's very, very similar. Well, it's the same as what I've just shown. So we've got least material requirement, and least material requirement is just basically the opposite of maximum material requirement. Right, dial test indicator, just put a quick slide in here for what DTI is from the comments that I've had on the previous GD&T training sessions. So we've got a DTI, dial test indicator, used at this location. So in this location we're using it on a lathe. It looks like we've got a 4-jaw chuck here actually, so you can actually push the jaws in different directions and adjust this quite easily without having to knock the part. So on this particular DTI, it looks like we're going from 0 to 0.2, 4, 6. So this sort of DTI might do 1.6 millimeter total travel, something like that. I also call these like a finger clock, and this a plunger clock, but they're basically DTIs. What you have to be careful on DTIs is you've got the stylus at this location. If you need to change the stylus, you need to change it with one of the same length. And why might you need to change the stylus? Sometimes when you use DTIs all the time and you're moving the DTI across the parts, these are quite hard, the actual material used for the stylus, but you sometimes get like a flat on the bit that you're using all the time. This ball at the end, you can get a flat on it, and that's when you lose the accuracy of the DTI, so you need to keep your eyes on that, and then you need to change this stylus to get the accuracy back. So it's just one thing to keep your eyes on. So in this case, if we were measuring run out, we'd put the part on the DTI here, we'd turn through 360 degrees, and then you measure the run out here. If this was total run out, we'd guide the clock across this surface at the same setting. So we're only moving this slide, we're not moving this slide. So it's only this slide we're moving, and we'd move it from this location to this location, and we'd measure the total run out there. If it's single run out, it would be done on this location. You'd spin it through 360 degrees and you measure the run out. Then you take the clock off, you move it to here, and you can measure the run out here. Take the clock off, measure the run out here. But the run out, they're here, here, and here. If it's a single run out, aren't linked. They're treated independently. If it's a total run out, you guide the clock across the surface, and it's all one zone. This is another DTI that I've used lots of times in the past. I usually call it a plunger clock actually. So we've got from this location here, we've got 0, 0.1 of a millimetre, 0.2 of a millimetre, and usually the travel on these sort of DTIs are about 10 millimetres travel you've got here. So you'd use this in a different location to this normally. One thing to note, some of the DTIs, the accuracies can change, the sizes of the clocks can change, but the accuracy can change as well. So on some DTIs you can get the distance from here to here can be only 0.025 or a thou, for example, rather than 0.2. So they're a lot more accurate. So then more accurate clocks you might use for clocking up on a cylindrical grinder, for example, something where you need that little bit more accuracy. So we've got on the right hand end a DTI being used on a milling machine. So in this case we're clocking up the fixed jaw of a vise. We're making sure that this fixed jaw on the vise is correct with the machine axis. So you'll move the handle for the machine and you'll move the vise in this direction and make sure it's clocked up 0, 0 all the way across. So it's used for milling blocks and things. One thing to note, when you put the vise on, you should really clock up down the fixed jaw as well to make sure this fixed jaw is true to the machine axis in this direction. Also, what you want to do, if someone's put the vise straight on the machine table, you ought to clock across the bottom of the vise here and here as well. Sometimes you'll put a parallel in here and you'll put the material on top to mill the top. And the reason why you should be checking this fixed jaw is because this one obviously moves and it's not as accurate as the fixed jaw. So if you're milling a block in here, the way you should mill it really, you'd put the block in, you'd sit it on this face, it'd be sticking up out the top, and then you're going to mill the face, and then the way to mill it square would be to mill the top face, and then you turn the face you've just milled against the fixed jaw, and then you'd probably put a round bar in on the movable jaw, and you push the round bar against the part, and basically what that does, it makes sure that the part is sitting against this jaw properly, and you can shimmy it out. You can test it with like a thou feeler blade or something in here to make sure the jaw you've machined is the face you've machined is up against this jaw properly. And then you mill the top again, and then you've got a face that is square, and then you can just mill the other two sides. But using the bar helps to make sure you keep the part square. Okay, so we've got this bottom view here, and this is quite important again. They're using a plunger clock on here to check to see if this surface is flat basically with the machine. It's not really the right DTI. I'd use more a finger clock like this on this surface because you want it quite accurate, and these are okay, but these tend to be more accurate than the plunger clock, where the travel on the clock is a lot less. So this is quite important to understand with regards to GD&T. Basically, the face that they're going to clock up should be your primary datum. So the face you clock up first is your primary datum. So in this case, if this is the first face that someone's going to clock up, this would be my primary face A, datum face A. Then if it's this that locates the disk, this would be datum B diameter. So I then put a clock in here and make sure the spindle is in the middle of this surface. So you clock this surface up and you move the machine and you zero the machine out. So you've got X and Y 0 at that center location. And that would be datum B. If this smaller hole is the diameter that locates the disk, you clock up this diameter instead and use that as datum B. But the important thing is the first face that you clock up is the datum A basically. And that's how you set the part up on the machine. So if you had datum C here, if you had to machine some holes in this relative to this hole here, for example, on this particular machine you can't actually spin the axis. So what you'd do is you'd put a round block at this location and a round block at this location through this T slot, and you'd push the block up against the part here and here. You make sure this is flat first and you'd probably shimmy it out, but then what you do is you undo these two bolts a fraction, you'd move the machine across to the right location of this hole, and then you'd physically rotate this part until this hole was at top dead center, for example. And that's how you'd set up datum C. Okay guys, many thanks for watching. Make sure you catch the next video.